Hello, gentlemen. Welcome back. I hope that you guys understood and did a good job with the last video and the practice problems. Again, if you have any questions about it or you had struggled through any of the problems, please email me so we can get those concerns taken care of right away. The purpose of this video is to look at graphs of equations. It's to look at x and y intercepts and how to find x and y intercepts, and we're going to talk a little bit about symmetry. So let's get started. Let's look at an equation. Okay, equation of two variables. Equation of two variables would be something like, y equals 6x plus 5, which we know is an equation of a straight line. Okay, and the two variables here are obviously y and x. We talk about the solutions to an equation. Point A, B is a solution, is if I plug that point into the equation, if I plug them in here, that the equation is true. Okay, and so, for example, the point 111 is a solution to the equation right here, because if I plug in the point 1 for x and 11 for y, I end up with 11 equals 11, which is a true statement. Now, a graph of an equation is the set of all points that are solutions. So this is just one particular solution, but there are many, many more. Obviously, another one would be 0, comma 5 is another solution. So the graph, which is a straight line here, is the set of all the points that satisfy this equation. Okay, and you should see that there's an infinite number of those. When we're talking about graphs, one of the things that we're interested in are x and y intercepts. And we can find, well, let's first talk about this. There's different options here. There's possibility we have no intercepts. We can certainly have no intercepts. We can have just one intercept for each x and y, or we could have multiple x and y intercepts. Okay, if we have multiple y intercepts, we're not going to be a function. We'll talk about more about that later. But we can certainly have more than one x intercept. Now, let me just give you a couple quick diagrams here if I can draw this pretty good. Here would be an example of a situation where we would have only a y-intercept. Okay, I don't have an x-intercept. All right, so I'd have no x-intercept, one y-intercept. I could have something down here where I have one of each, like a line. Okay, or I could actually have something that has many intercepts. I could do something like this. Okay, so there are three different options that we can have in terms of intercepts. Let me get rid of those. Now let's talk about how we're going to actually find these intercepts. Okay, and let's go to the next thing. So if I want to find the x-intercept, I want to set y to be equal to 0. Okay, so in the equation we had before, y equals 6x plus 5. If I want to find the x-intercept, I would solve the equation. I would set this y to 0, so I would go 0 equals 6x plus 5, and then I would solve that for x. Okay, and you guys can all do that. If I wanted to find the y-intercept, I would set x equal to 0, okay, and then solve the equation for y. So again, if I'm looking at that particular problem and I wanted to do it for find the y-intercept, I would say that y is equal to 0 plus 5. Okay, because if I plugged in 0 for x, I would get 0. And so I'd get right here, my y-intercept is 5. Okay, and we knew that already because that's in slope-intercept form. Okay, let's do an example. Okay, let's find the x and y intercepts of this equation, and then take a look at what its graph looks like. So the first thing I want to do is find the x-intercept. I let y be equal to 0. So if I let y equal 0, I come down to this. I should notice here that I can do a little factoring to make my life a little bit easier. If I factor here, I can take out a 2x squared out of both. And so I have two terms multiplied together, and so that the result is 0. That means either this term right here or this term right there is going to be 0. And hopefully you guys would see that means that x is either going to be equal to 0 or is x is equal to 2. Because if I plug in 2, I get 0 here. If I plug in 0, I get 0 there. Okay? And that means that I have two x-intercepts, one at 0, 0, and the other at 2, 0. Now if I want to look at what the y-intercepts are, we want to let x be equal to 0 and solve for y. So if I plug in 0 for x into the above equation up here, this term's going to be 0, this term's going to be 0, and so what we should see is that the y-intercept is at 0, and I have 0, 0. Okay? And if I look at what this graph looks like, it's a cubic function. Let me get rid of that. Those marks there. Okay? And I see that I have a 0, 0. That's an x and a y-intercept because it hits both. And then the other one is right there at 2, 0. Okay? So that's pretty straightforward in terms of how to find intercepts. Let's talk about symmetry. We're going to talk about three types of symmetry. First we're going to talk about x-axis symmetry. The graph is symmetric about the x-axis if the point xy is on the graph, then x negative y is also on the graph. Okay, so the key here is if I have this point on the graph, then this one is also on the graph. Okay, we're going to talk about testing it, and then I'm going to show you some examples. I'll show you an example here. So if I want to test for x-axis symmetry, I want to replace y with negative y in the equation. So wherever I see a y, I'm going to replace with a negative y. And if I get the same equation back, if I get an equivalent equation, then the graph is symmetric about the x-axis. Sounds confusing, but it really isn't. Let's do an example, and then you can see what I'm talking about. I want to show that the equation x minus y squared is equal to 0 is symmetric about the x-axis. So what does that mean? That means that I first have to replace y with negative y. So if I do that, I get the following. I get x minus negative y squared is equal to 0. Now let's look at this term here. This is really negative 1 squared times y squared. Well, we know that because I'm squaring it, I'm just going to get the positive value here, y squared. Okay, so negative y squared and y squared is the same exact thing. This is my original equation right there. And because it's the original equation, okay, I can say that this is going to be symmetric about the x-axis. Okay, and let's see what that looks like. Let's erase that. Let's erase that. It's going to look like this. Now let's see what happens here. I have the point 0, 0. I have the point here 1, 1. Down here I have the point 1, negative 1. Okay? Again, what did we say? We said that if xy was on the graph, then x, negative y was on the graph. And you can see how it's just a mirror image across the x-axis. All right? This is the point 4, 2. And then down here, another point 4, negative 2. Okay? Again, it's just a flip. I'm following along these lines right there. Okay? Hopefully that makes sense. Let's talk about y-axis symmetry. Okay? A graph is symmetric about the y-axis if whenever we have xy is on the graph, then negative xy is also on the graph. Okay? A function that's symmetric about the y-axis is called even. All right? So we're going to hear about even and odd functions. An even function is symmetric about the y-axis. Let's talk about how we're going to find if something's going to be symmetric about the y-axis. This time we're going to replace x with negative x in the equation. If I come back and I get the same as the original equation, then we're symmetric about the y-axis. Okay? Easiest way to see it, let's do an example. Here's my equation, x squared minus y is equal to 0. I want to show that this is symmetric about the y-axis. Or another way to state this is to show that this is an even function. So I replace x with negative x, and if I do that, I get this. And just like we talked about in the last problem, this term is the same as x squared, because when I go negative 1 squared, I get positive 1. So I can say that these two are the same. This equation right here is the same as this one. And because it is, I can say that, whoops, go back. Because it is the same as the original equation, I can say that I'm symmetric about the y-axis. All right? And let's see what a graph something looks like that. And so here's something that looks like a mirror image across the y-axis. That's what you would think about symmetry. So here I have the point 1, comma 1. And over here I have the point negative 1, comma 1. And again, let's remember what we said. We said if xy is on the curve and we're symmetric about the y-axis, then negative xy is on the graph as well. And as you can see, that's going to be the case. And that's symmetry about the y-axis. Okay. The last one I want to talk about is symmetry about the origin. Okay. If we're symmetric about the origin, we're talking about xy is on the graph, then negative x, negative y is also on the graph. These functions, if you're symmetric about the origin, we're talking about what we call it as an odd function. Okay. Again, let's look at the rule. How do we test? We want to test for origin symmetry. We're going to replace both things. We're going to replace x with negative x and y with negative y. If we get the same equation, if we get an equivalent equation, then the graph is going to be symmetric about the origin. Let's look at an example. Y is equal to x cubed. I want to show that it's symmetric about the origin. So again, if it's going to be symmetric about the origin, I have to replace x with negative x, y with negative y. Then let's simplify and see what we get. So I get negative y equals negative x cubed. If I simplify, I get negative x, whoops, went too fast. Negative x, negative y, I'm sorry, is equal to negative x cubed. Because remember, this is like negative 1 cubed. Negative 1 cubed is negative 1. So this statements are equivalent. Now note I have a negative and a negative on both sides. And what I can do is I can cancel them out. And I get y is equal to x cubed, which is exactly the same as my original equation. And because it is, I can say that the graph is symmetric about the origin. And so let's look at what that looks like. Looks like this. And so if I'm looking at this point here, this point is 1, comma 1. And now I got negative 1, comma negative 1 here. This point up here is 2, comma 8. Oops. And down here, I'm 2, comma negative 8. Okay? And remember, what's the rule? The rule is if x, comma y is on the graph, then negative x, comma negative y is on the graph. And again, you can see that that is definitely the case in this situation. Okay? So we looked at symmetry there. Here is some practice that I want you guys to take care of before you move on to the next video. One is the read section 1.2. There's another video that's going to accompany 1.2 on circles. But pay attention to these examples that I have there. They're important. Again, I'm going to have you looking at examples because they can show you solutions on how to do things. These practice problems, these first ones right here, all have to do with the new stuff, the new information, 83, 85, 86, and 87, all have to do with some review stuff that you've done in the past. I want to make sure you understand. And again, if you have questions, you need to email me, and we can talk about what you're struggling with. Okay. Let's just summarize again. So again, we talked about graphs of equations. Graphs of equations are basically those points that satisfy the given equation, the set of all the points that are solutions to a given equation. We talked about how to find x and y intercepts, and then we talked about symmetry. We talked about symmetry about the x-axis. We talked about symmetry about the y-axis. We talked about symmetry about the origin. We talked about even and odd functions. Okay, so make sure you guys understand that. Make sure you email me if you have any questions. Make sure that you do those practice problems and before you move on to the next section. Okay, have a good day, John.